Okay, I will share the slides. Okay, so today I'm going to talk about the part two of the Tiger Graph best practices. So, so in the beginning, I will talk about some housekeeping items. So even you are muted, just feel free to post your questions in the QA tab anytime. And then I will try to answer all the questions there in the end of the session so that I can make sure the recording of the this session is smooth. Okay, so because this webinar is recorded and the content will post it in YouTube after this session so that you can also review it later. And right, and if you have any questions, you can also post your, you have any issues, you can also post your issues in the chat as well. Okay, so, okay, yeah, then let me introduce myself first. So I'm Jinyu Chang. I'm the Director of Customer Solutions at Tiger Graph. I've been with the company for about 7.5 years and almost 8 years actually. So I graduated from Kent State University from the master program. And during the 7 years, I also co-authored the GSQL query language. I developed a lot of like key features of the GSQL query language. And also I engaged with many major customers, either lead the solution project or delivered the solutions myself. Okay, so and also our team, the team I'm leading, we have built the graph algorithm library and a lot of like anti-fraud and anti-money laundering applications. Okay, so that's myself. So today's agenda is I will talk about the query writing best practices incorporating the system architecture, because every decision we want to make during the query writing is highly related to how the system is architectured, right? How we run things in parallel, how we perform the massive parallel processing is decides what's the best way to write your GSQL query. Okay, so in the beginning, I will touch some basics of accumulators and also select statement basics. And then I will talk about how the system functions parallelly, what's the parallel processing mechanism, and its applications. How does that impact your way of query writing? And then I'll talk about the distributed computing mechanism, and then based on that, how we write the query, right? And then I will talk about the memory composition and some memory optimization techniques. And in the end, I will talk about some other techniques that will be that I'm sure will be very useful for you. Okay, so let's start with the basics. Accumulators and select statements. So as we all know that Tiger Graph adopted this MPP architecture. It's a massive parallel processing. So inside the Tiger Graph, the graph database, each vertex or edge is a computational unit. What does that mean? That means the calculations can be performed in parallel or distributed from each vertex or edge being traversed. That means we are running some computation on all the millions and the millions vertex and edges being traversed at the same time, right? All the computation happens in parallel. And also that means like because we are running all these logics concurrently at the same time, right? That means at the same time, for the same variable, its value also can be updated from multiple vertices or multiple edges. So from the chart on the right, you can see that so first the example, like we are updating the same variable stored on the vertex, because a variable can be stored either on the vertex or global memory, right? And the first chart is when the variable is stored on the vertex, we can update it from multiple edges, right? If a variable is stored in the global memory outside the graph, then we can also update it from either multiple edges or multiple vertices. Okay, and also each vertex can update the variables on its own, but this will be single-threaded, right? But the other cases are all happens in parallel. So that means since we are changing the value on the vertex from so many different places, that means we need a function that, or we need a way to be able to handle this concurrent value update, right? So in Tiger Graph, we actually adopted the Prego model that we update the values in the map reduce way. That means if it comes to map reduce, that means we need to define an aggregation function to handle the multiple updates. And in the end, based on the aggregate function, we aggregate all the incoming values into the updated value of that vertex, right? So that's the formula I put on the left. So here V prime is the original value of the variable, and the M1 to MK are all the messages it received from the multiple edges or vertices. And then through the aggregation function F, we get a new value of the variable. Okay, so that is how it works. So because the parallel processing and this the need of having an aggregation function, that's why we have something in the query language that is very important. It's called accumulators. Accumulator is a special type of variables that accumulate information about the graph during the traversal. Okay, so that is a special variable that can take multiple values and aggregate all the values. Okay, so to assign a value to accumulator, let's say we have an accumulator out here on the right, then we can send some value from each edge that has been traversed. Let's say we are traversing from D, right? And from every edge, I want to assign a value to this accumulator. So there are two phases to assign new value to the accumulator. The first one is we collect all the values being that we want to update to, on this variable or accumulator, right? That's the phase one. And in phase two, based on the aggregation function, we calculate a new value for the accumulator. So for this case, the aggregation function does sum, right? So we sum all the values received from the multiple places, then we get a new value for the accumulator. So this is how accumulator works. So as a metaphor, it's kind of like in a scenario or example, like a teacher in the classroom, right? A teacher may collect all the test papers from all the students and calculates the average score, right? So it's exactly the same way how accumulator works. So the first thing, so in this case, the teacher is the accumulator and the student is vertex or edges. So the test papers are the messages sent to the accumulator, right? So in order for the teacher to calculate the average score, it takes two phases. So first phase, teacher will collect all the test papers. And the second phase, teacher would grade it and calculate the average score. This is exactly how accumulator works in the context of parallel processing. Okay, so so as I mentioned, a variable may be stored on either on the vertex or in the global memory, so that we have two different types of accumulators. That we have local accumulator starts with single at sign, and we also have global accumulator start with double at signs. A local accumulator are stored on each vertex you have traversed. You can see it is on each vertex, and the global accumulator is outside the graph. It's in the global memory. So usually we define global accumulators to store the information regarding a graph or subgraph, right? And we store the information about individual vertices on a local accumulator. Okay, so based on how we, and also I mentioned like we have aggregation function, right? So based on different aggregation functions, we also have many different type of accumulators. So each of them has their own way of aggregating the incoming and the original values, incoming messages and the original values. For example, we have sum accum, max accum, min accum, and average accum. So like for example, the old value, original value of sum accum is 2 and you received 135. Then after the aggregation, the new value will be 11, right? And for max accum, the old value is 2. And then after receiving the new messages, we found that the max value is actually 5, right? Then we got 5 as its new value. So in the same way, min accum keeps the minimum value, average accum keeps the average value. And also we have, other than scalar types, we also have container types, right? For container types, we have set accum, it's unordered unique elements, right? It puts everything being received into a set. And also we have a list accum, it's a sequential collection of elements. It keeps some order, but think about this, because we are receiving the messages in parallel, so that the order of messages, the order of receiving the message is actually cannot guaranteed. So in the parallel context, the list accum doesn't actually guarantee the order, right? But in the sequential context, it guarantees the order. I will talk about later more about like when things are more sequential and when things are in parallel. And for map accum is a key value store, and heap is ordered tuples, right? You can keep the top k ordered elements. So this is the concept of accumulators. And another thing I have to mention is the select statement. Once you understand the concept of accumulator, and then you also know how to write good select statement, I think you are like a 70% success, right, in writing the perfect GSQL code, right? Because GSQL is nothing but traversal, run the traversal on the graph, right? And when we run the traversal on the graph, it's nothing but traverse from one set of vertex to another set of vertex. And the select statement is just a one hop or multiple hops that you want to traverse on the graph, right? Once you know how to do that, then things will, you actually know most of the GSQL query language. Okay, so now, so for a single select statement, one thing that is, so in this webinar, I won't touch everything, right? I only want to touch some very critical, some critical points. For example, the accum clause, right? So because accum clause kind of is something, comparing to other query languages, accum clause is something like a kind of like unique in the GSQL query language. And the meaning of the accum clause is it defines the calculation that happens on each edge or vertex being selected. That means we will define some calculation in the accum clause. So in this case, we define some assignation to a specific double @ sign global accumulators, right? That means each edge we traverse will perform this logic concurrently. Okay, so for example, what this query does is it will find the age distribution of friends that were registered in 2018, assuming we have a social graph, right? We have input user and also is a friend of user A, B, C, D. Okay, and we want to find out how many friends are in their 20s, how many friends are in their 30s, how many friends are in their 40s. That's the question, right? So if you look at the query, it takes the user as an input. So this is definitely the best practice to start from vertices like this. That is, we create a vertex set named start. So start is a set of vertex, and it takes the parameter as its initial value. In this way, we can find the input user immediately, right? So because I do see some like a beginner GSQL writers, they would say where ID equals to the input. So that will just make a full scan of the entire type. So this is a recommended way to start from a specific vertex. Okay, and then let's look more about this accum clause. So this in the accum clause, we have defined a map accum using integer as key and the sum as its a value type, right? And then we assign the value to this map accum, with the key is the age of target node divided by 10. So t dot age means, so t here are the target node, meaning A, B, C, D, right? And dot age, meaning the age stored on them, that's 25 for user A, 28 for user B, and divide by 10, that's their bucket, right? They are at 20s or 30s. And then 1 is the count that of the user we have found that falls into a specific bucket, right? So that means when after this logic is put after accum clause, that means this logic will happen on all the edges. Of course, where clause happens before that, this is also concurrently happens. It will filter the right edge to perform the accum clause, right? And once where clause is done, we start to run accum on all the edges at the same time, right? So for this edge between input user and user A, T means user A, right? Then the age of user A is 25, then 25 by 10 is 2. Then we will send the 2 as a key, 1 as value to the map, right? And so we do the same thing for every edges being selected at the same time and push the value into the accumulator. That's the phase 1, right? And then there is after the accum clause, there's a hidden aggregate phase that we will aggregate all the received key values into the map. And then after that, we know the result. Like there are 2 friends in their 20s and and 1 friend in their 30s. Okay, this is how accumulator works. All right, and also how accum clause works, right? And also this is the example how we can update a global accumulator from multiple edges concurrently. And this is a different example. Well, I think I'll skip this one. This is just another example how we update accumulators on vertices from multiple edges. It's a pretty much the similar thing. Okay. And this is an example of post-accum. As we know that accum means the logic defined in accum will execute from all the edges selected, right? And what post-accum means, the logic defined in post-accum will execute at the same time from the edges mentioned in the post-accum. You can see that in line 10, we have a post-accum referring vertex T, right? T is the alias of the target node here, right? That's on line 8. If you look at line 8, this is where T is defined, meaning our target node. So that means the logic we have defined on line 10 will execute on the target node of the selection, right? And then now we can see target node is actually target node of friends 1 hop. And the friends 1 hop are the user A, B, C, D. They are selected from the input, right? You can see that in line 6, friends 1 hop is start from the input and the traverse to their friend. So that the definition of 1 hop is A, B, C, D. And here, and then we have at line 7, we started a new select statement traversing to second hop friend, E, F, G, right? And then, so that means the logic in line 10 will be executed on the target node of 1 hop vertex, meaning this logic will be performed on E, F, G at the same time, right? Okay, so I won't go through the whole lot of details regarding the the details of this query. But the point I want to make here is the logic we have defined in post accum similar to accum that will be executed concurrently on the vertices being referred. Okay, so here refer to T alias, and here we refer to S alias. Okay, and if you are interested in learn more about the select statement, we have a whole series of webinar regarding this that is also available on YouTube. Just search for GSQL lectures. Okay. Okay, so now let's start to talk about the parallel processing mechanism and its applications. Okay, so in order to talk about the parallel processing mechanism, we have to discuss how the data is actually stored under the hood. Okay, so under the hood, we have three types of data. I think in the previous part that the schema design best practice, I talked a lot about how ID service works, how we map the external ID to the internal ID, and in the actual graph, they are all in the internal ID format, right? So that is the actual graph is actually the vertex partitions and the edge partitions. So we have vertex partitions start with their internal ID, and also the vertex attributes stored in the vertex partitions. Basically, the internal ID of the vertex and their attributes. And we also have edge partitions. Edge partitions has the source vertex ID and the target vertex ID, right? And also their edge attributes. Basically, we store the vertex and the edge separately, okay? And once we have these three type of data, they are actually segmented and spread out across different servers, right? We split each type of data into segments, and the segments are stored distributedly across the cluster. And the segment of different components with the same ID actually stores the data for the same set of vertices. For example, if today I have vertex with this internal ID, and its ID info, its vertex info, its neighbor info, they will be all on the same server and also belongs to the corresponding segments with the same like a sequence number, right? Like for example, all the information of this vertex will be in segment 8 for ID service segment 8 for vertex segment, also segment 8 for edge segment. And in each segment, there will be a relatively large number of vertices in each segment. Okay, and this vertex is just one of them. Okay, so this is how the data is stored. Okay, so once we know that the data is stored in that way, and then the next question we want to discuss is how we handle the parallel processing, right? Let's say we have a server with 4 CPU cores, and then usually we telegraph system will maintain thread pool with equivalent number of thread based on the CPU cores. So that means if we have 4 CPU cores, we will have 4 threads in the thread pool. Okay, and then now let's run some logic. Say, hey, I want to start from all the users, and then we want to run some logic in the post accum for each user. So the first thing the system will do is we will find all the segments, the vertex segments that belongs to the user, that is under the user type, and then based on number of thread in the thread pool, we will pick 4 segments to be processed at the same time. And you can see that here, between the segments, the job is done concurrently, but within each segment, the job is done actually sequentially, right? So this is how we parallelize the process with multiple CPU cores. So right now, if we look at this, let's say if the thread has been assigned to segment 6, were able to finish its job earlier, right? Then it will move to the next unprocessed segment to continue to do the work until all segments are processed. So this is we handle so this is how post-accum works, right? And in the same way, if you put the logic in accum, again, we would find all the segments having the containing the edges being selected, right? And then assign the threads from the thread pool until all the segments are finished. And also in the same way, if you have a distributed environment, let's say we have two servers that stores, each server will take maybe half of the segments, right? And then in the same way, two servers will try to utilize all the CPU thread in order to process the query concurrently. And of course, you may have questions, say, hey, what if I don't want the system to exhaust all the CPU resources to serve one single query? That is definitely possible because we support to make the configuration change to say, hey, I want to limit the thread number for a specific vertex. You can configure that from the part of the header when you send the request, okay? So that you can have multiple queries running without conflict too much with each other, okay? So this is how we run things concurrently, right? And then because the system functions in a way that we try to process all the logics defined for each vertex and the edge at the same time, right? Then that means when we write a query, we need to be careful to make sure that the logic we programmed in the GSQL query language is utilize the resource as much as possible, right? Let's look at the example. Let's say if we want to write a cosine similarity algorithm, right? And one possible way of doing that is you can see that first we can define a vertex set, and we start from a specific vertex type, right? And then we collect the vertices under that type to the set. And then we can say, hey, for each vertex in the vertex set, I want to perform this calculation, right? So in this case, usually this way of writing query is not quite recommended. The reason is the logic outside the select statement are executed sequentially on the master node. Okay, so that means everything within the for each loop body will be executed sequentially because everything outside the select statement is actually sequential. There's only one thread handling the whole process. Okay, and so that's why usually it's not a good idea to write a query in this way because it's not good for utilizing the system resources. Okay, so other than that, we also have other ways of writing the query. For example, we can write a query to calculate the cosine similarity of a vertex as a subquery, right? It takes a vertex as an input and does all the job inside this single query. And then we can call that subquery from the accum clause, right? So this way, the subquery is executed from the accum clause. That means we will run this subquery parallelly, in parallel, right? But one thing we need to think about is, so of course, this approach does utilize the system resource a lot, right? So the performance can be good, but there are pros and cons, right? So the pros of writing a query this way is only number of threads of subqueries are running at the same time. So that is very memory efficient. So let's think about this. Why only number of threads of subqueries are running at the same time? Yeah, I think the answer is because it's under accum, right? And as I mentioned, like when we run accum, we will assign the thread to each segment at the same time, right? So in this case, if we run that query in this server, So 4 subqueries will be executed at the same time, right, on this server. So that, and also each subquery is pretty lightweighted. So that means this approach will be very memory efficient. You only have the memory usage of 4 queries, the number of thread queries at the same time, right? And upon the finish of each subquery, the memory will be released. So the memory is very good, and each subquery is very easy to implement, and it's very lightweighted. That's the pros of this approach. However, the cons of this approach can also be performance problem, because think about this: if we are calculating topological cosine similarity, let's say each vertex will calculate its cosine similarity, like we say, we want to calculate cosine similarity between A and B, right, based on the common neighborhood. Let's say one of the neighborhood has like thousands of neighbors. So that means we are going to run the cosine similarity algorithm subquery for each neighbor of this intermediate node, right? So that means all the rest part of the neighbors are traversed exactly 1,000 times. So that's n squared complexity when we for some cases when you run the query in a query calling query way, right? That will just take you a lot of time, right? So so that's the pros and cons. But however, what if your edge is only traversed very limited times if you do run a query calling query? So the situation will be much better, right? So that means when we implement the query in the query calling query way, then we need to think about what's the complexity, right? If the complexity can be essentially low, then I think that's a good idea. But if it gives you n squared complexity, then it may take very long to execute, right? Okay. And then next thing is, so what's the best way of doing that, of writing the query? Then the most recommended way usually is you run all the vertices together with a heavier data structure, so that you can differentiate where the data, based on this data structure, which vertex is coming from, right? So one good example is our actually the graph algorithm implementation of the cosine similarity. You can see it's a relatively more complex than other way of writing the queries. But the pro is really is mostly efficient, and you only traverse the graph once. But the cons is a little bit difficult to implement. You need to really think through, if I start from everybody, how should we structure your accumulators so that we keep the information for every vertex we're starting from, right? And also the query will become more memory intensive, because we need to keep the information for so many vertices, right? However, this can be mitigated. I'll talk about this when I talk about how do we implement the memory or optimize the query. Okay, so another thing that is highly related to how the data is stored and how we execute the query in parallel. That is the hub node, right? As we know that all the edges of a specific vertex will be stored in the same segment. And when we execute the query, same segment will be assigned to only one thread, right? That means all the edge logic or vertex logic in the same segment will be processed in parallel. No, sorry, sequentially, because only one thread, right? So that means if we have a hub node with with a huge number of neighbors, and only one thread is assigned to that segment, right? That means all the huge amount of edges will be processed sequentially. That may potentially becomes a performance bottleneck, right? So, so in that case, there are a few different ways that you can mitigate the situation of a hub node. For example, if you want to write a query that only gives approximated result, right? Then you can consider just the filter them out. Because for a lot of cases, when we run some analytic to detect the hub nodes, right, we found that there are actually some abnormal values. For example, they are a space, they are a null value, right? And then I think the best thing we can do is we can just remove them, right? And also another thing we can do is we can filter them out during our traversal, because in a lot of analytics, the hub node doesn't give you a lot of meaningful info, because if two vertices are shared, are connected through the same hub node, the hub node also connects a few million other vertices, right? Then the connection is not as meaningful if you connected through some other node with fewer neighbors, right? Because fewer neighbors will give you more valuable information, while hub node usually doesn't, right? So the best, so one possible thing we can do is we can use where clause to filter those hub nodes out, so that your queries can be significantly accelerated. In my experience of running those anti-resolution solutions, like usually if you want to filter, by filtering out those hub nodes can make your solution run like 100 times faster. So it's very important. And sometimes you say, hey, I do want to keep some of the info from the hub node. It's meaningful to me. Then another thing you possibly could do is use the sample clause, right? So in this sample clause, it says if a hub node has alt degree or neighbors more than 1,000,000, right? And then I only want to sample 100 neighbors from it. Then in this case, you without having to traverse each neighbor of hub node, you only sample 100 to traverse. That's another thing we can consider. And also, we can also optimize the schema to mitigate this situation, right? Because as we know, all edges of hub node are in the same segment. But however, if we can split the neighbors in some way, for example, we can split the transactions by days, right? Or can split any like monitor signals by hours, right? That essentially has split the hub node into like a smaller vertices by introducing an intermediate connection. In that case, then each intermediate vertex will be fall into different segments, so that the load of the hub node is actually spread out across multiple segments. In this case, things will become more parallel for you after doing this change. Okay, so that's how our parallel processing works, and also how that may impact our way of writing the GSQL query. Okay. And next, I'm going to talk about the distributed computing mechanism and its applications. So in Tiger Graph, there are two, for a GSQL query, there are two execution modes. One is single server mode, and the other one is a distributed mode. And for the single server mode, actually the only difference is like you have a keyword to choose between either single server mode or distributed mode. Distributed mode is a distributed keyword. Like when you write a query, it starts with create, query name, and the parameters, right? And if you want to build a distributed query, all you need to do is just create distributed query name, and the rest of stuff, right? Just one single keyword to switch between different modes. And the underlying mechanism is as follows. So for single server mode, like the cluster will choose one server to be the master node of that query. For example, in our case, server 2 becomes master node of that query. So, oh yes, when it comes to master node, I want to add something more. It's like in Tiger Graph cluster itself, we don't have any, they're all equivalent. All nodes are equivalent. But when we run queries, one server will be elected as the master node when you execute that query task. Okay, so in our case, server 2 becomes the master node of that query task. And when we do the traversal, however, server 2 doesn't have all the data. You can see that we have stored the graph distributedly, right? Then during the traversal happens, on server 2, server 2 has to fetch the needed graph segments from server 1 and the server 3 in order to finish the calculation. Okay, so usually single server mode is better when you run something like small queries. A query only traverses very few numbers, smaller numbers of vertex and edges. Then single server mode usually give you a better performance. And then we also have distributed mode. So distributed mode also again is the same thing that one node will be elected as the master node. We run the query, and the master node will coordinate all the other nodes to finish this job together, right? The calculation will happen on all the servers, and even we have one node as the master node, and all the sequential processes outside the select statement will be executed on the master node. And all the logic inside the select statement, like for example, accum, post accum, they will be run distributedly across all the servers. And each server will take care of the vertices and the edges has been stored on themselves. Okay. And okay, so let me see. Right, and the computations execute on all servers in one replica. So that means if you have enabled a high availability, right, you have multiple replicas in your cluster. So then when you the distributed calculation actually only happens within one replica. And when you run the queries, the global accumulators are synchronized across the cluster. Okay, so for example, in one select statement, I updated the global accumulator, right? So what the system will do is it will update the local copy of your global accumulator. And then after the select statement, the system will try to synchronize all the changes from multiple server to one place, and then update each local copy on every server, right? So it's kind of like a pretty expensive process to maintain all the global accumulators up to date. Okay, so usually distributed query are better for those queries that traverse very large amount of the graph, very large portion of the graph. For example, if you start from all the vertices or start from a certain type of vertices, then usually it's very good to select a distributed mode to execute your query task. And of course, on our roadmap, we will be able to judge that automatically by the language itself to run in distributed mode or single server mode. Okay, so based on this execution model of Tiger Graph, single server mode or distributed mode, right? So here are a few things that we want to consider when we write our queries. So first is don't traverse large portion of the graph when you are in single server mode. Otherwise, the query will run out of memory due to large graph has been shuffled to one server, right? Think about this. Let's say if today we run things on a single server mode, right? And we start from all vertices. That means we're going to shuffle all vertices into one server, right? Then hopefully we will run out of memory. And when we are in distributed mode, then we should limit the size of a global accumulator, since full copy of the global accumulator will be maintained on each server in the replica. So that means if we are in distributed mode, and let's say we want to keep a huge data structure to store some info for all vertices, then that means all vertices of all the info will be copied to all the servers, right? That's going to be very memory intensive. And another thing is accessing target vertex, including accumulators and attribute, is more expensive than accessing source vertex, accumulator, or edge attribute. What does that mean? Like if you look at this diagram, we know that we have server 1, 2, and 3. They store the data distributedly. And like say, we want to traverse vertex 1 to its neighbor and access its target attributes, the attributes of 2, 99, 37, and 61. And the attribute of those vertices can be anywhere. It can be on server 1, like say in this example, 2's vertex attribute is on server 1, right? However, 99, 61, 37 might be on other servers. So that means it will trigger shuffling when you try to access the target node attribute. So that also means it will be more expensive than accessing only the source vertex attribute and edge attribute. Yeah, because if you think about the source vertex attribute, all the vertex attribute of 1 will be on the server 1, right? Because it's together with the edge. Yeah, so that's something to think about. So another question is, okay, so given this mechanism, right, like a distributed computing mechanism, should we choose more servers with smaller RAM of each server, or less server with more RAM on each server? So this is actually a very interesting question, and this is also a frequently asked question. So my answer usually is, depends on what kind of task you plan to run, execute, right? If you want to run a lot of real-time queries, store the data distributedly will inevitably introduce you like a overhead of shuffling the data, right? So if you want to run real-time queries, I would recommend you use like fewer servers with higher RAM, and if possible, you can add a few replicas, because adding replicas will sequentially improve the query per second or throughput of your real-time queries, right? But when you run like a batch queries, for example, if you want to run PageRank, then it's recommended to add more servers, but the server number, of course, we want them to be within the reasonable range, right? For example, based on our benchmark, we have tested the performance of PageRank with 2, 4, 8 servers, and we observed almost linear increase of the performance. But usually, I won't recommend like your server number exceed 20 also. Yeah, because that's a safe that's a safe number to keep your number of servers within that range, because we don't want to, the more servers you have, the more shuffling you may do, right? Okay. Okay, and this is the memory composition. So I just talked about the distributed computing, and now I'm going to talk about the memory composition and the memory optimization. Okay, so this is the memory composition of the Tegra graph system. You can see the most memory consuming parts are the GPE, graph process engine, and the GSE. As we know, GSE is the bidirectional ID mapping, right? External ID to internal ID, and the GPE actually takes most of the memory because we store all the vertex and the edge segments in GPE, and also all the query memory utilization is also with GPE. Okay, and if we look into every query, the memory composition is like a global accumulators will take a major part, and also so are the local accumulators, right? And the shuffling also takes some space. And other than that, there are some more minor stuff. For example, the vertex set you activate right now, or the graph update will also take some memory. Okay, so given this, there are a few tricks and the knowledge we need to know when we write our queries, right? The system has 2 memory states. Usually it's a normal state. We don't have to mention that. It just to handle everything normally. And also we have alert state and the critical state. So during the alert state by default is 30% of free system memory. Okay, so when the system has less than 30% of the free memory, the system will enter alert state. And during the alert state, the loading performance will be decreased to prevent from overusage of the memory, okay? And then when the system has less than 10% of the free memory, it will enter the critical state. Critical state will abort all the loading job and the queries in order to prevent the system from crashing, Okay, so these two states are actually configurable. You can use a different number other than 30% and 10%. But sometimes if you observe your system, hey, my loading is really slow, my loading hangs, my query got aborted due to critical state, right? Then maybe it's time for you to think about, are we in the healthy state of the memory, right? And if you do see that sometimes your query return with error message saying, hey, critical state is aborted, then this is something that you may want to consider to do. That is to split the query into mini batches. Okay, so when to do that? So for example, when your query involves really significant fraction of all vertices, traversing large number of vertices, and all the vertices will store a very large amount local accumulators or global accumulators, then that's the timing, and you are getting the critical state error, right? Then that's the time you think about how to split your query into mini batches. So the way of doing that is we'll take an integer k. K means that we are splitting the query logic into k mini batches. Okay, and here then this, and we want to split the logic into mini batch with this for each loop. You can see the for each loop will perform exactly k times, and in the beginning of every iteration, it will start from all the vertices we want to process and only select whose ID mode by k equals to I. I is the number of iteration. Okay, so that we only keep one case of the vertices in the mini batch to run through the job, right? And then every time when I'm done with my iteration, I want to clear things out. So that means every time I take a part of the vertices to process them, and then we clear things out in the end. Okay, so this will make things a lot memory efficient. However, it will be smaller. You might be slower, but it's kind of like we trade the speed performance for memory, right? But usually it works pretty well. Okay, so that's how we can so that's the memory composition of the system, and also how the technique to split the query into mini batches. And the last thing I want to mention here is checking the logs for your query execution. That is almost the most fundamental and the important skill when you when you try to identify the bottleneck of the query, no matter it's a memory bottleneck or a performance bottleneck. Okay, so right now we are looking at some logs from the GPE log, right? Usually GPE log is located here. And if you search for the request ID, so this part, the red part is the request ID, right? You will find all the execution flow of the of this query. And from this log, you will see a lot of useful information. For example, when the queries get started, when the query is finished, right? And when it's finished, what's the query execution time, right? And then it also show you how many iterations it has taken. So here by iteration here, it means nothing but a select statement, right? So that means in this query, we have run through 3 select statements, and the first select statement traverses 2 edges. 2 edges means 2 accum, right? And the 2 vertices reduced, that means 2 post accum. Execute the 2 accum and 2 post accum, and what's the time for each? And then from here, you can see, oh, like when your query has performance issue, you are able to tell, okay, one select statement takes 90% of time. I want to look into it. What is this doing? Is there any way that I can make it easier to traverse less vertex, or is there any way that I can make the accumulators being used more lightweighted, right? Then from this log, it can give you so much information that to troubleshoot your query. Okay, and another useful thing I want to mention is the log statement. With this log statement, you can see that because in this query log, every line has some keyword called UDF. colon, colon, right? And then you can also use this log statement to print log for you so that you know, sometimes you write a query with like say while loop, right? Then we kind of lost track from the log, which iteration is which select statement. It's become hard to tell, right? But with this log statement, it allows you to print log almost everywhere in this query, right? Then you just, for example, I have a select statement here. Then I can say, hey, print start to collect info for user vertex, and then you run the select statement, and then print finish collecting info for the user vertex. Then that will definitely enrich your log printing and it makes your troubleshooting job a lot easier. So that's how we can utilize the logs. Okay, so now let me look through the questions and try to answer them. Okay. Within the select, are accumulators being on the left-hand side of assignments on arrays? Now I'm reading the question from Dana. With the select statement, with the select, are accumulators limited to being on the left-hand side of assignments to avoid the risk condition on arrays? Oh, actually reading doesn't have risk condition because we are like kind of like a map reduce style. Like before the select statement finished, the value of the accumulator will remain as its original value. So there is no locks or risk conditions for arrays. So because in the example, I only show you how to assign the values to accumulators, but whenever you read them, there is no risk condition and the performance should be pretty good. Okay. And let me look at other questions. Could you clarify the difference between accum and post-accum? I think as I mentioned that the difference is really like sometimes accum perform exactly the same as a post-accum. Like when you write a select statement, you didn't like specify any edges, then the logic on the accum will just happen on all the vertices. So it becomes very similar to post-accum. But when you run accum for a select statement with edge traversal, then that's become very different, right? Then in that case, the accum will happen on all the edges, and post-accum will happen on the vertices being referred to. Okay, and let me see. Within the select, our accum, oh, that has been asked actually. Could you clarify? Okay. The difference between accumulator and the aggregate. Well, the type of accumulator decides the way of aggregation, right? Like I mentioned in this slide. Yeah, so we have different type of accumulators. So so each of them has their unique way of aggregating the messages. So that's really the like when you define an accumulator, just choose the different like say aggregate type, like for example max accum and min accum, then it will do the aggregation accordingly. Okay. Let me see the next question. Is it recommended approach just to traverse the incremental load edges? For example, data came in the past 3 days. Yes. So yeah, I would say yes, because this is really based on specific use case, right? If the past 3 days data is enough for you, then you do the traversal on them, then that could be a good idea. But in that case, we better design a schema. Either we index the dates or find a way that we are able to only traverse, narrow the searching space down to the past 3 days. Then I think it could be a good idea. Yeah. Let me see the next question. What's the use of critical state being set to 10% if so much activity fully stopped? I think that's the major motivation is to prevent the system from fully crash. Because if the system got crashed and then you bring it up, it will have to load all the data from disk to memory. It takes a while to warm up. So, and also abort some queries that resulted in this critical state will release the space for the further analysis. Okay. Okay, then that's all the questions. Let me jump to the last slides.
And Jinyu, there's actually one more Q&A in the the Q&A part. So it's next to maybe the chat, or I'll ask it if you don't see it. It's within a select, are accumulators limited to being on the left-hand side of oh, I guess you're right. Left-hand side assignments.
Yeah,
Okay.
I will answer that one, right? You can also access their values just like you access to any like attributes as well. Yeah. Okay, now let's jump to the last few slides. So yeah, I do encourage you to try out Telegraph if you haven't yet. Like we have Telegraph Cloud, like you can start a spin up a free instance, and also you can download the enterprise edition. We have up to 50 gigabyte free version. That means you can ingest up to 100 gig of data and try it out, right? And we also have test drive demos that we have loaded the graph up to 4 billion edges. You can experience our amazing performance from there as well. And also I encourage you to take our certification test for like a Telegraph fundamentals and also algorithm certification. And then you can also join the community, help others, and also like post your questions there. Okay, and yeah, this is Cloud. Yeah, thank you for participating this this session, and looking forward to see you again.
Yeah, thank you all so much. Have a great day. We'll send you this in an email with the PowerPoint and the recording. Thanks. Bye.